This is joint work with Claire Mathieu in Paris, and we'll be talking about a stream of graph edges and graph problem, in particular variations of max click. So we're looking at large clusters in a graph, and specifically on social graphs, which is a class of specific graphs which have a degree distribution of a certain kind. Now, the context is the existence of giant components in random graphs, first in the Herder-Shreni model, then in a model where the degree distribution is arbitrary. And then our algorithm will essentially keep k uniform sample edges. That will be a random graph, and it will observe the giant components in this random graph. And we will show the main result is a detection, the existence of a gamma delta cluster. If the graph has a cluster and k is square root of n log n, then the algorithm will accept with high probability. And then for a random graph that follows this degree distribution, mu, then if the graph does not have a cluster, the algorithm will check with high probability. Now, there will be other results on lower bound and the reconstruction of the cluster and the extension to dynamic graph, but the essential message is that finding such cluster is not so hard on social graph. So let's suppose you have a stream of edges, E1, E2, En, and let's define what a gamma delta cluster is. So S is a subset of the vertices. And we have two conditions. We want the internal edges of S to be large. So gamma times the maximum number of edges. So in a sense, the first condition is that S is a gamma click or gamma cluster. And the second condition is S is large, which is the size of S is greater than delta square root of n. So you can see that if I take the parameters 1 and 1 for gamma and delta, then it means that the max click has a value square root of n. And we know that it is hard even in this case. And then we also now know that it is very hard to approximate. That goes back to Hashtag in the 20s. The goal of the paper is to show that it is not so hard on social graphs. What is a social graph? So for example, the Twitter graph were generated from tweets. So imagine you have these tweets here with an author and a content. Then the nodes are the tags. And here we have two edges from the author to each of the tags of the message. And the observation is that this graph have a heavy tail degree distribution. So for us, we'll take this hypothesis that the probability that the degree is I. This is equal to C over I squared. And then naturally you have this degree sequence. So the number of nodes of degree 1 is Cn, number of nodes of degree 2 is Cn over 4, and so on and so forth. So here are a typical example. In the middle here we have a social graph, a Twitter graph actually, with 10,000 edges, probably recovered in 10 minutes, roughly. And then here we have to the right k uniform random edges, and we can see that we observed clusters in the original graph, and then we have here a large connected component in the samples. Actually, we have two large connected components, and there is a link between these two things. Okay, so what is our algorithm? Our algorithm is extremely simple, probably as simple as possible, you can imagine. We just sample with a very classical technique called reservoir sampling. So everyone knows this algorithm in computer science, but in data science, maybe it's not so well known, in the sense that we do not store the edges. We're going to make the random edges on the fly, so to speak. And the algorithm is simply you just initialize the k first edges, and then for all I greater than k, then you're going to keep the E sub I edge with probability k over I. And And then in case you keep it, then you replace a random E sub j of the reservoir by E sub I. And then our algorithm maintains k of size square root of n log n and observes the giant components of the reservoir. If you have a large connected component, then you accept, otherwise you reject. So the key to the approach is the correspondence between random graph and giant components. So let me recall what a giant component is. It's a connected component, which is a constant fraction of the size n. And in case of the Erdős-Rényi graphs, where all edges are taken with constant probability p, then we know that we have a giant component if p is greater than 1 over n. And we extend modestly this result in the sense that if you start with a gamma cluster instead of a complete graph, then p has to be greater than 1 over gamma n if you want to observe a giant component. Now, if you start with the distribution mu, where the degree follows a natural law, like the power law, then there is this configuration model where essentially you start with each node with its degree, which is called a half edge or stub, and then you make a matching between the stubs and you obtain a graph on the right. And then Moller-Reed gave sufficient condition in 2008 to observe giant components that we're going to use. So our model is the combination of these two previous models. First, we generate a graph that has a degree distribution with the configuration model, and then we sample uniformly, exactly like Erdős-Rényi. So we combine the two, and we ask which condition ensure that we have giant components. So here, very precisely, here is the algorithm to detect the existence of a gamma delta cluster. K now, of course, slightly depends on gamma delta. And then the threshold on the size of the giant component is this function, which is n to the 1/8. And then our main results are this one-way stochastic approximation. If the graph has a cluster, we have to accept with high probability. And if we take a random graph from mu with no cluster, we have to reject with high probability. And notice that here we use a red marker for high probability because it's not the same probabilistic space as in this case. In this case, it is a choice of the algorithm, choice of sampling, and in this case, it is a product of taking a random graph from you with the sampling of the algorithm. So let's do the first result. So here is the simplest argument. So remember that what is the probability that an edge is taken in a reservoir? It's k over n. Now develop k over m with k equal to what we took. M is this value. And naturally, we find 1 over gamma delta square root of n. And then by definition, the size of S is greater than delta square root of n. So this is greater than 1 over gamma, the size of S. And then we use the previous result that if P is 1 over gamma n, and here being the size of S, then we observe a giant component. So indeed, we do have, with high probability, a giant component in this case. Now, what happens if we take a random graph from mu? So first observation is that there is no large gamma cluster in this particular case. And then I omit the proof. And then assume this is true, then how are we going to approach the problem? Then first, so we're going to show that indeed the algorithm rejects with high probability. And to do this, we are going to apply the Moller-Reed condition. So the Moller-Reed conditions are, actually there are several conditions. The degree distribution has to be well behaved, and then there is this quantity Q of D. And if you satisfy this condition, then there is no large connected component. So the analysis is that now the degree distribution is probabilistic, which is a difficulty because it comes from the sampling. So we have to analyze first the expectation of the degree distribution. And in this case, we can check that it follows the monomid condition. And then we have to construct a different vision of the configuration model, which is a key idea. One of the key ideas of the paper is that you start with a particular degree distribution here on the left. And then in our model, we do the matching first because we do the configuration model first, and then we do the sampling. So we're going to invert these two sampling procedure because they are independent. So we're going to do sampling first here and matching after. And because they're independent, we obtain the same result. So essentially, we analyze the monoid condition with high probability, and for this, we'll produce a deterministic degree sequence that will perform this condition, and then we will eventually, once we have this degree distribution, that implies the property with high probability, and then we have that the probability that the large connected component has a size greater than this parameter, then this is going to be close to 1. So we will conclude that the reservoir has no giant component with high probability by mono read, and then because the graph has no large gamma cluster, the detection algorithm is correct with high probability. Okay, so there will be some other result. So first of all, we will show a lower bound on the space. So for example, we're going to show that we need square root of n. Square root of n is necessary. And our algorithm uses square root of n log n, so it's not so bad. And here we use a known reduction from a very classical problem, which is a multi-party disjointness problem. Okay, so given essentially such an instance, for example, you have an instance like this, so you have a q vectors, Boolean vectors of size n, and you want to know if they have a line where all the values are 1. Okay, so that's the disjointness of these vectors. And then the classical reduction from these authors in 2012 is to reduce this problem to a graph problem where if you have a disjointness, then there is a clique here in this graph, which is the case here. And the size of this graph is square root of n. So therefore, because you have a lower bound of disjointness, you imply a lower bound on this particular problem. Okay, now next result is to suppose you want to approximate the clique or the gamma cluster. So let's suppose you have a gamma cluster, so of size square root of n, delta square root of n. Observe what you have in the reservoir. So you have a large connected component by one of the results. And then what you're going to do is take the two cores. So eliminate the nodes of degree 1 repeatedly. So you end up with it. And then we show that this is a good approximation of the cluster, at least when gamma is 1. Okay. And then the next generalization is the generalization on dynamic graph. We're going to take windows, sliding windows, and generalize the result. So in conclusion, we studied the existence of large clusters, and essentially we provided a streaming algorithm with space square root of n log n, which is a good approximation. The main tool we use is this one-way stochastic approximation. So if the graph has a cluster we accept with high probability, and if the graph is taken randomly from this distribution and has no cluster, we reject with hyperlink.